We want to express S9 in terms of S8, which is given in the problem statement. So let's compare the subsets that we get from the integers 1, 2, all the way up to 8 to the subsets that we get from 1 through 9. We're going to compare the complex power sum of all the subsets of 1 through 8, and we'll find the complex power sum of all the subsets of 1 through 9. This includes the complex power sum of all the subsets of 1 through 8 and the complex power sum of those same subsets with 9 appended to them. So for example, one contribution to S8 will be the complex power sum of the subset 2, 7. In S9, we will also find the complex power sum of 2, 7 and 2, 7, 9. Let's look at an easier example, and let's find S sub 2. This is going to be the sum over all the subsets of 1, 2 of the complex power sums. The subsets of 1, 2 are 1, 2, and 1, 2. The complex power set for this subset has a sub 1 is equal to 1, so this is just I. For the second subset, a sub 1 is equal to 2, so the complex power sum is 2 times I. For this last subset, we have a1 is equal to 1, a2 is equal to 2, so the complex power sum is I plus 2I squared. Adding these, we'll get S2. This is 4I plus 2I squared. Let's now compare this to S sub 3. This is going to be the sum over all the subsets of the complex power sum of 1, 2, 3. All the subsets of 1, 2 are also subsets of 1, 2, 3. So I'll reproduce those here. And we get I, 2I, and 1 plus 2I squared again. There's a one-to-one correspondence between these subsets and the subsets that include 3. I'll list them here. And let's calculate these complex power sums. Here we have I plus 3I squared. This is 2I plus 3I squared. And this is I plus 2I squared plus 3I cubed. We have one more subset of 1, 2, 3, and that's 3. We can think of 3 as corresponding to the empty set. The complex power set of the empty set is not defined, but we can just assume for the purposes here that it's equal to 0. It won't contribute to S3. So this CPS is 3I. Let's calculate S3. First we have this 4I plus 2I squared that we got from S2. This gets repeated over here by these first few terms in our subsets. So we also have 4I plus 2I squared a second time. Now we have 3I. We have 2 of these 3I squareds and 1 3I cubed. So we can say that S3 is 2 times S2. And in order to generalize this, we can see that we're taking 3 times a power of I that depends on the number of elements in each subset. Here with this 3I cubed, we have 3 elements. This is because it corresponds to this 2-element subset of S2. The I squared comes from the fact that we have 2 elements in these subsets, which corresponds to the single element subsets of S2. We have 2 of these 3I squareds, so if we were to count this, it would be 2 choose 1, the number of ways of choosing one element in a subset out of 2. We just have 1 3I cubed. That's because there's only one way of choosing 2 elements out of our set that also contains 2 elements. That's 2 choose 2. Finally, up here, we just have 1 3I. That's 2 choose 0 times 3I, because that's the number of ways of choosing 0 elements out of 2. This will be the same for any consecutive values of S sub n. So for S sub 9, we're going to have 2 times S sub 8. We have 8 choose 0 ways of choosing 0 elements out of 8 for the empty set. And that complex power sum will be 9 times I. Subsets with just one element in them, that's 8 choose 1. The coefficient of I squared is 9, and so on. Let's write this as a summation. K goes from 0 to 8. 8 choose K. Then we have 9 times I to the power of K plus 1. This is given in the problem statement, so let's focus on the summation. And let's factor out 9I. This leaves I to the power of K. You might remember that 1 plus I to the 8th power. We can write this using the binomial theorem, which is what we have up above. So we can write this as 9I times 1 plus I to the 8th power. You should know some properties of the product of complex numbers. For example, the argument of the product of 2 complex numbers, and the argument is just the angle that it makes with the real axis. This is equal to the sum of the arguments of the 2 complex numbers that you're multiplying. So for example, for 1 plus I, our argument is pi over 4. So the argument of the 8th power of 1 plus I is 8 times pi over 4, or 2 pi. This means that 1 plus I to the 8th power is a real number. You should also know that when we multiply two complex numbers, the magnitude of the product is the product of the magnitudes. The magnitude of 1 plus I is root 2. So the magnitude of the 8th power is 16. This gives us that 1 plus I to the 8th power is equal to 16. And so our sum is 9I times 16, or 144I. And now we can calculate S9. In the problem statement, S8 is negative 176 minus 64I. This adds up to negative 352 plus 16I. So our answer is 368. If you'd like me to solve any other math contest problems, please leave them in the comments.